Thank you for joining GG413 Geological Data Analysis. This series of videos will go through some example non-parametric tests. In this video in particular, we're going to cover the sign test, which is a one-sample test of the central value of a population. So the sign test is a test of mean and median if the sampled population is symmetrical. And it's a test of the median if the population distribution is not symmetric. So let's get right in with example 2-7. Which is a measurement, it involves a measurement of salinity. So it's N equals 15 measurements of salinity. And the question being asked is whether the central value of the population sampled has a mean greater than or equal to some known value, some test value. So in that situation, the null hypothesis is whether the central value, and I'm writing this tilde for median, if the median salinity of the population sampled is greater than or equal to some test value, mu, and that test value in the example is 98.5 parts per trillion. And the null hypothesis is therefore the median value is less than mu. And we're going to define alpha, the significance level, as 1%. So the overall strategy is as follows. So if the median of the sampled population is the same as mu, then we would expect the probability of taking a sample and finding a value greater than mu to be 0.5. So little p is 0.5, and it describes the probability of making a measurement greater than mu. It's the probability of success for a single trial. And so what we're going to do is calculate the probability that out of n samples or n measurements or n tries, what's the probability of r of them being greater than 0.5, or I'm sorry, greater than mu. And that will have a binomial distribution. So the p is the probability of r out of n tries successfully meeting the criteria that the values are greater than, not greater than or equal to, greater than mu. And we're going to compare p to alpha. So this is going to turn out to be a test using the binomial distribution. Right? So if we sketch the binomial distribution, the horizontal axes are successes, the number of measurements exceeding mu, and the vertical axis is p. And let me sort of sketch this distribution. It's a discrete distribution, so I got to draw these steps. And so it's going to turn out to be a left-tailed test. So in the right-hand tail, if the population sampled has a greater central value, then a lot of the measurements will fall. The R will tend to be in this region. Between the two tails, this would be where we would expect R to fall if mu S, the median of the sampled population, is about equal to mu. And so the critical test, so the test is in this lower left-hand corner, because if we find it's in this left-hand corner, then we can reject this null hypothesis. We want to always define alpha as the region where the null hypothesis can be rejected. So the procedure is step A, count the number of measurements whose value is greater than mu. And Wessel says you can assign them pluses. Okay, and any values equal to mu are discarded, because it will turn out that n, or yes, n, the number of tries, is equal to the sample size minus the discarded values. I'm sorry, the sample size minus the number of discarded samples. So if there are, 5 values that equal mu, then you would subtract 5 from the sample size to get n. So once you've done that, okay, so this defines R. Okay, that's the number of successful measurements greater than mu, and this defines n, right? And so big P, as you may recall, is n over R times little p raised to the r power times 1 minus p raised to the n minus r power. And remember, little p is equal to 0.5, right? So 1 minus p is the same as p. So this equals n over r, in parentheses, the binomial coefficients, times p to the n. And that's, of course, n over r times 0.5 to the n. So in our example, p is equal to 0.5, we already knew that, but r is equal to 2. There are 2 samples who have salinity greater than 98.5, and n is equal to 14. Now remember, we want, I didn't quite state this right, so we want the cumulative probability, the area under this curve, and to define alpha, not just p of any given r. We want the cumulative p for r less than or equal to the determined value of r. So the probability of r less than or equal to 2, the cumulative probability, is therefore the binomial coefficient for no successes, no value is greater than 98.5, plus the binomial coefficient for one value exceeding 98.5, plus, not plus and minus, the binomial coefficient for two successes, all times 0.5 to the 14th power, and we get a cumulative probability of 0.0065. And we therefore find that the probability of finding an R value equal to what we found and less is less than 0.01. So we must reject H0. In other words, the number of successes we found is so unusually improbable, it's less than our significance level. Therefore, it's very unlikely that the salinity of our sampled population is equal to mu or greater than mu. Now you'll recall in the special circumstance where the number of samples is, the sample size is large, or more formally when NP is greater than 5, the binomial distribution can be well approximated by a normal distribution. And so the z value that you would use here is r minus the expected value, or the mean, which is mu times p, divided by the standard deviation, which is np over 1 minus p, the square root of np times 1 minus p. And with p equals 0.5, this turns into 2r minus n over the square root of n. And the critical z value can be found from a table. And this is a one-tailed test, so the critical value is z sub alpha. Okay, so that includes our first non-parametric test, the one sample test of a central value.